So hey there, welcome back to another video of a Monotech YouTube channel. In this video, I'll be talking about what is self-attention of a vision transformer. So starting out the video, the self-attention mechanism is a key component of the transformer architecture, which is used to capture long-range dependencies and contextual information in the input data. The self-attention mechanism allows a VIT model to attend to different regions of the input data based on their relevance to the task at hand. Therefore, the self-attention mechanism computes a weighted sum of the input data where weights are computed on similarity between the input features. This allows the model to give more importance to them. So this was the basically the thing is, therefore, the self-attention mechanism computes a weighted sum of the input data where the weights are the weights are computed based on the similarity between the input features. This allows the model to give more importance to the relevant input features, which helps it to capture more informative representations of the input data. Hence, self-attention is a computational primitive used to quantify pairwise entity interactions that help a network to learn the hierarchies and alignments present inside the input data. Attention has proven to be a key element for vision networks to achieve higher robustness. So the next question which arises and which comes in mind is, what are attention maps of VIT? The attention maps of vision transformer VIT are matrices that represent the importance of different parts of an input image to different parts of the model's learned representations. In VIT, the entire image of the input data is first divided into non-overlapping patches, which are then flattened and fed into the transformer encoder. More about the architecture below. Attention maps refer to the visualizations of the attention weights that are calculated between each token or patch in the image and all other tokens. These attention maps are calculated using a self-attention mechanism, which each token attends to all other tokens to obtain a weighted sum of their representations. The attention maps can be visualized as a grid of heat maps where each heat map represents the attention weights between a given token and all other tokens. The brighter the token color of a pixel in the heat map, the higher the attention weight between the corresponding tokens. By analyzing the attention maps, we can gain insights into which parts of the image are most important for the classification task at hand. Vision transformer VIT architecture. This is the next section we'll talk about. So, several vision transformer models have been proposed in the literature. The overall structure of the vision transformer architecture consists of the following steps. The first one is split an image into patches, fixed sizes. Number two, flatten the image patches. Number three, create lower dimensional linear embeddings from these flattened patches. Number four, include positional embeddings. Number five, feed the sequence as an input to a state of the art transformer encoder. Number six, pre-train the VIT model with image labels, which is then fully supervised on a big data set. Number seven, fine tune the downstream data set to for image classification. So, vision transformers VIT is an architecture that uses self-attention mechanisms to process images. The vision transformer architecture consists of a series of transformer blocks. Each transformer block consists of two sublayers, a multi-head self-attention layer and a feed-forward layer. The self-attention layer calculates attention weights for each pixel in the image based on its relationship with all other pixels, while the field forward layer applies a nonlinear transformation to the output of the self-attention layer. The multi-head attention extends this mechanism by allowing the model to attend to different parts of the input sequence simultaneously. VIT also includes an additional patch embedding layer which divides the image into fixed size patches and maps each patch to a high dimensional vector representation. These patch embeddings are then fed into the transformer blocks for further processing. The final output of the VIT architecture is a class prediction obtained by passing the output of the last transformer block through a classification head, which typically consists of a single connected layer. So the next thing is, while the VIT full transformer architecture is a promising option for a vision processing task, the performance of VIT's vision transformers in image recognition is still inferior to that of similar sized seen in convolutional neural networks. Alternatives such as ResNet, when trained from scratch on a mid-sized dataset as ImageNet. Overall, the VIT, which is a vision transformer architecture, allows for a more flexible and efficient way to process images without relying on predefined handcrafted features.